So what we're going to try to do is start. This is not definitive. We're going to get into more of this next term. But we're going to start trying to piece these elementary steps together into a reaction sequence. Remember in general chemistry, when you were working on kinetics, you had elementary steps. Those elementary steps were not recognizable in the overall reaction because they happened right in here. Those elementary steps happened in here. Organic chemistry is a little bit modified. You can get single mechanisms, single step mechanisms in organic chemistry. But most often there are 2 or 3 or more steps in the reaction. And we're going to approach it in a similar fashion, trying to understand how these elementary steps fit together in terms of kinetics. Which one happens the fastest? I think that's a practical matter. Maybe they tried to approach it from a thermodynamic angle at one point, but since organic reactions happen, most of them pretty slow anyway, thermodynamics is not the best approach because they have different rates of reaction too. So that's our angle of approach is kinetics. Okay. Remember, we're going to use SN2, SN, well, let's see, I think they put them in this order. SN2E2. Oops. E2. SN1 and E1. And then we'll also introduce some of the other of those 10 or 11 elementary steps. But these are our main focus, those reactions. And remember what this means. This means bimolecular. This means nucleophilic. And this means substitution. So bimolecular simply means that 2 molecules come together, and that's the reaction. Whereas when we say SN1, that's unimolecular. And the one molecule does something first. It's counterintuitive. This is a single step. This is a single step. This is a 2-step. And this is a 2-step. Okay, keep that in mind. So for this reminder here, this SN2 reaction, we have a nucleophile attacking the carbon that's attached to a leaving group. And this happens in a simultaneously. Nucleophile attacks the carbon and the leaving group leaves. That's an SN2 reaction. And of course, the carbon with the leaving group on is called a substrate. But it's the nucleophile attacks the electrophile, and the electrophile is the substrate. For the SN1 in contrast, and these are just reminder slides, the leaving group goes first. And we're going to talk about this a little bit later in the slide set, but just to point this out so it'll be whirling around in the back of your head. As far as the rates of reaction go, this first step is very slow compared to all the other steps. Right? The leaving group essentially doesn't want to leave because it's leaving behind a carbocation, which is very unstable. So the leaving group has to be a very good leaving group in order to make this happen. And then once you've got the carbocation, then the nucleophile attacks the carbon. And we get the substitution for the leaving group that's already left. But we'll also point out the fact that that leaving group is a negative charge and the carbocation is a positive charge. So the leaving group's not going to go very far. Right? The bond may break, but you've still got the formal charges that are attracting one another. So whichever side the molecule the leaving group leaves from, it's going to stay close to. Okay, that has a bearing on stereochemistry later. I just thought I'd point that out now, so it wouldn't be a big shock once we get there. But both of them are substitution reactions. And this slide just emphasizes the fact that what we're looking at here in this two-step process is invisible to our any of the tools we have, right? This is a proposed mechanism that explains the reaction outcomes. And that very often is the main reason that we propose SN1 versus SN2, because the outcomes are recognizably different than one. We propose one way, we propose another way. Which one agrees with the outcome? That's where we go. And that's the way kinetics has always worked, right? You remember general chemistry kinetics, you'll have mechanisms, multi-step mechanisms that are proposed for an overall reaction, and you'll have maybe 5, 6, 7, 8 of them. And you just start Xing them out, chopping them out. This one won't work, that one won't work. You work your way down to maybe 2, and then you have to make a choice. So that's what we're talking about here. The overall reaction gives us the same outcome for either the SN1 or the SN2. On the surface, it looks like that, but we haven't included stereochemistry yet. That's to come. All right, when we look at the energy diagram for an SN1 reaction, we see that since it's unimolecular, that is, the leaving group leaves, and that takes a certain amount of energy. So we're gonna start off, and we're gonna end up here at a transition state. And once the leaving group leaves, all of the players involved are at a slightly lower energy level than the activation energy for this reaction. So it takes a lot of energy to get there, but you get into this trough. And that's a momentary stability point. Then just a little bit more energy, and there you go, finish the reaction. I like this drawing because it fits the production of nitroglycerin very well. Nitroglycerin, you have to put a lot of energy into it, get it over this hump, but now it's sitting here. The nitroglycerin molecule is sitting right here. And if you just look at it cross-eyed, it'll go over that hump and you get your explosion. So it's kind of like a metastable state. And that's because the carbocations are very unstable. And the step that goes from the carbocation here with its SN2 hybridization. It took me a second. No, not SN2. SP2, sorry. SP2 hybridization, it's trigonal planar. This carbocation is very unstable, so it only takes a little bit of energy to get it over the hump. And remember, when we were talking about rates of reaction, the rates of reaction are dependent upon activation energy. So this activation energy here is much greater. So it takes a lot of energy to get to this point, but once you get to that point, the reaction proceeds really fast. So remember what we said about reaction mechanisms in general chemistry. The slow step is the rate determining step. So the rate for this reaction, this SN1 reaction, is determined by this, where the leaving group leaves. That's the slow step. That determines the rate. Okay. Elimination reactions. What do elimination reactions? What are characteristics of elimination reactions? You lose a hydrogen, and the electrons from that bond breaking, that heterolysis, go to make a double bond between the neighboring carbons, the alpha and the beta carbons. That's what an E2 looks like. So this base attacks the hydrogen. And why didn't it attack the other side where the leaving group is? Probably because the leaving group is a good electron withdrawer. And it makes that hydrogen more positive. So that's where the base wants to go. So it takes that hydrogen, and the curly arrows show you that you're forming a double bond. And then when you do that, you've got 5 bonds to a carbon, and that can't work. So the leaving group has to go. So that's an E2 reaction where you have a single step, but it's bimolecular. Right? Remember when we talked about molecularity? Unimolecular, bimolecular, termolecular. Those are the possibilities. Unimolecular, there's only one molecule involved. Bimolecular, the 2 molecules involved. They have to collide with enough energy and at the correct orientation to happen. Termolecular is almost impossible because you've got to get 3 molecules coming together at just the right angles, just the right energy to happen. So termolecular is almost like forbidden. We only go to termolecular when nothing else works. Okay, so this is an E2 reaction. You end up with a double bond. You end up with a pi bond, and your leaving group is gone. Plus, the base has captured a hydrogen. Okay. For an E1 reaction, we would have to form the carbocation by the leaving group going. And then once you've got the carbocation, the base will take the hydrogen. You have heterolysis of that hydrogen, carbon-hydrogen bond, and those electrons go to make the double bond. That's an E1 reaction. So this is an overall E1 reaction, produces the same thing as an E2 at first glance, right? Again, we have not introduced any concepts concerning stereochemistry or, stereochemistry, right? And double bond, pi bonds work into that too. It's a type of stereochemistry. Okay. So for this E1, you got a similar situation, right? The leaving group leaves, takes a lot of energy, very slow, and you end up at an intermediate with a carbocation. Now, that example of carbocation, what type of carbocation is that? Primary, secondary, tertiary. It's tertiary, right? It's attached to 3 other carbons, right? So that stabilizes it. Still, it takes a lot of energy to get there. And then once you're there, then the base can attack the hydrogen. We would, I'm just thinking logically, why didn't the base go around and attack that positive, right? Because negatives attract positives. Well, for one thing, there's steric hindrance, right? You've got 2 methyl groups in the way. It's going to have a hard time getting in there. Whereas that hydrogen, it still has a slightly positive charge on it, right? That's the easiest one to pluck off. And besides, this is an elimination reaction, right? Maybe under certain circumstances, it would go in there and do that. But that would be a substitution, wouldn't it? If the leaving group leaves and the base attaches itself to that carbon, that's not an E1 reaction, right? So we're categorizing our reactions, and that forces us to approach it as a proton transfer rather than a substitution. Right? So it may very well do that other reaction, but it won't be called an E1 then. And it won't produce a double bond either. All right. I mentioned this earlier, and this has to do with reaction kinetics and rate laws. If we look at the rate laws for the various reactions, and since I've already got them on the board, let's write them up there one at a time. So with an SN2 reaction, you're going to have the rate's going to be determined by the concentration of the nucleophile and the substrate. Right? So this rate over here is going to have its K and the nucleophile plus the substrate. I'm not sure how they write it. They write it differently. Yeah, they did the nu minus and the R. That includes their leaving group. Okay, that makes sense. Let's do it their way. There's your leaving group. And this has a negative formal charge. That makes a good base. Okay. So why do we only have a unitary order here and order there? You remember when we were talking about elementary steps? Well, when I was talking about elementary steps, say general chemistry, if you go back and look at the reaction, SN1, let's go back to SN1. Here we go. SN1. There we go. Is that, no, SN2, excuse me. SN2. If this is an elementary step, we can derive the orders of the reactants from the reaction itself, from the coefficients. Right? We only have one nucleophile and one substrate. So that means their orders are 1 and 1. Recall that overall reactions that are a composite of elementary steps, you cannot determine that except experimentally. But the elementary steps you can derive from their balanced equations. Right? I hope whoever taught you general chemistry made that point. Okay, let's go back to here. All right, that's an SN2. SN1 here, the rate determining step is the one that includes the leading group. So this is only going to be dependent upon that. And these are different Ks. I'm not writing the subscripts in there. E2 is bimolecular. So it's going to be dependent upon the base. And why do we call it a base rather than nucleophile? Because it's going for a proton. Right? It's a Bronsted-Lowry base. It's going for a proton. In one circumstance, we might consider it a base. In other circumstances, we might call it a nucleophile. But they have similar characteristics either way. And then for the E1, the rate is determined by the slowest step. Right? So they have that in common. Now these constants, each one of these is going to be different depending on the reaction. So I'm not saying that all those Ks are the same. Now, what this tells us, this gives us information as to what type of reaction is it. I mean, we can determine that we've got a pi bond after the reaction than before, so maybe it's an E1 or an E2, and then we say, what's the rate determining step? Right? Or what's the rate law? The rate law tells us that the rate's only dependent upon this one. It has to be an E1. If it's dependent upon the base concentration and this one, then it's an E2. So that's the logic, the stream of logic that takes you to the correct mechanism. Okay. So I already said that. And I mentioned this one earlier. Remember, the rate determining step is the slowest step in a mechanism. So one that's the slowest, and we showed that in our energy diagram. The slowest step for the SN1 and E1 is the one where the leaving group leaves. So this is SN2. Because this mechanism consists of just a single step, it has to be the rate determining step. So we have to include both of them to determine the rate. Because it is a single step. Bimolecular, though, single step. Bisingle, let's see. Bisingle, single bi. If you need a way to keep them separated. Okay. Whereas in SN1, the slow step is going to be the leaving group leaving. And it all has to do with that energy barrier. I mentioned this earlier. That there's a huge energy barrier for the leaving group leaving. That makes it the slow step in the reaction. And the second step happens really fast. And so, excuse me, similarly for the E2 versus E1, the E2 being a concerted single step reaction, you have to include both concentrations to determine the rate. Whereas the E1, we only need the leaving group step to determine the rate of the reaction. And this is just a rehash. I mentioned it already a couple of times. Unimolecular versus bimolecular. Unimolecular means there's only one molecule involved in that elementary step. And that's the SN1 and E1. Remember this one? It looks a little different the way I presented it in general chemistry. This is Arrhenius equation. It relates this term right here to both the temperature, and C is not concentration in this one. This C is just a constant. T is the absolute temperature at which the reaction occurs. So you see the T term is both in the, well, down here, down below, and up in the exponent. And that's e to the negative delta G over RT. I think the way I presented it, it was e to the negative activation energy over RT. There are slight differences there. Now, what does that tell us about the reaction? Well, the rate constant, if you're looking at what the rate constant is, you have to take into consideration the temperature, right? As the temperature increases, the reaction rate increases. The rate constant changes, rate constant increases. Remember, all of these steps are constant only for a given temperature. If you change the temperature, then you change the rate. So the constant will get larger and the rate will increase. The rate of reaction will increase if you increase the temperature. But if you increase the activation energy, Based upon where it is in that formula, you decrease the reaction rate. Right? This is the mathematical treatment of that statement. The energy diagram we showed earlier is like a pictorial, logical, semi-quantitative approach that sometimes connects better, unless you just love these mathematical equations. Okay, this reminds you that the rate law is experimentally determined. The elementary steps of the rate law are combined into the overall reaction. And I like to think of them as occurring inside the arrow. But so for the elementary steps, those coefficients can be inserted as exponents in the elementary step rate law. Those are the orders of the elementary steps. Okay, that's why we have a 1 for each one of those components in the elementary rate laws for the SN2, SN1, and for the E2 and the E1. Now, this is the next issue, stereochemistry. If you start off, your reactant has a stereocenter, then depending on which reaction it undergoes, it may retain that stereochemistry. It may flip the stereochemistry, from R to S, or it may produce a mixture of stereoisomers. They could be enantiomers, they could be distereomers. It depends on other factors. So it can get complicated, but understanding what happens during each reaction will help you understand which stereochemistry is more likely. So a blanket statement at this point says that, I don't think we need this anymore. A blanket statement at this point says that the stereochemistry of the reaction for an SN reaction, SN1 reaction, is different than that of an SN2. And likewise, an E2 is different than an E1. And the primary cause for that is that if the leaving group leaves from a stereocenter, that's no longer stereocenter anymore, right? Because the carbocation now is sp2 hybridized. It's trigonal planar. And it's not that's not a stereocenter. But the product of the subsequent step, since the SN1 and the E1 are two-step reactions, the subsequent step, you could get a front side attack or a back side attack and give you a mixture of stereochemistries for the SN1 and E1s. Okay, let's look at those examples here. I think I've already mentioned this. I'll just put this in a single statement. Up to this point, we've looked at stereochemistry of freestanding molecules. But now we're going to talk about stereochemistry in terms of reactions. Right? The outcome of a reaction is a stereochemistry in itself. And what it will do is help us determine what stereoisomers are produced from a reaction. If we know what type of reaction it is, we can predict the outcome. If we have the outcome instead, then that information can tell us, by the proportions of the stereoisomers, can tell us what type of reaction we elementary step we started with. I can break a tie, so to speak. So here's an example of an SN2 reaction. All right, so this is bimolecular, and the attack and the leaving group are going. This has happened at exactly the same time. So the substitution takes place on the opposite side of the leaving group. Right? In this case, we've got S, 1-chloro, 1-phenylethane. And the iodine is the attacking group. It's the nucleophile. The chloride will be the leaving group. So which side will it attack on? Since the chloride's coming out at you, right, it's in the way. So the iodine's going to attack from the back side. So when it substitutes for the chlorine, it's going to be the opposite stereochemistry. Now your stereocenter is going to be R and not S. For this example, okay, it's like flipping your umbrella inside out in a strong wind. This has a name, of course. It's called a Walden inversion. I guess that's the name of whoever studied the thing in the first place. This is known as a backside attack. Now, another reason it doesn't attack from the front side is electrical repulsion, right? Because that chloride, the leaving group, is slightly negative to start with. Now the iodine's coming in, it's slightly negative, or it's got a whole negative charge, and it's going to be repelled by the chloride. So even though you've got steric hindrance on the backside with that methyl and the phenyl group, you're still going to have a backside attack. The rate of the reaction may be very slow. That's entirely possible. But the preferential attack is going to be backside and reverse the stereochemistry. Okay. This describes what a front side attack would look like. And it has two things working against it. I've mentioned those already: steric hindrance and charge repulsion. So it doesn't occur. I shouldn't say it doesn't occur. It's very unlikely, right? If you make an absolute statement like that, then somebody's going to find an exception. So it's very unlikely. Now the author says does not occur. I guess he's pretty confident. He's a better organic chemist than I am. And this slide just gives you an idea of the electron repulsion on one side, and the other side introduces you to steric hindrance. No, it's not. It's just charge repulsion. Front side attack would be charge repulsion. Backside attack is more positive. So it's going to be more attractive to the nucleophile. Okay, so let's look at this reaction. It looks to me like we have two stereocenters. Right, we have one with a methyl group attached and one with the bromine attached. Well, if we're considering this in terms of an SN2 mechanism, then that sulfhydryl nucleophile has to attack the carbon that's attached to the bromine, has to break the bromine. Bromine's the leaving group. Okay. So we remind ourselves that there's only one step involved in this reaction, and we have to show the curved arrows in such a way that we do this all in one step, right? And stay within the 3-arrow rule. 3 curly arrow max rule. Okay. So this sulfhydryl group is very electron rich. It's definitely a nucleophile. Bromine's a good leaving group. So the SN2 would attack from the backside, and that would give the attached SH group would give it an opposite stereochemistry. So how would we represent that with curly arrows? We have the tail of the arrow, either from a bond or from a lone pair. So this is from a lone pair, attacks that carbon, and the bond breaks. Heterolysis sends that electron pair to the bromine. Bromine comes off as a negative ion, and the sulfhydryl group is now attached on the backside. So it flips the hydrogen forward, and the sulfhydryl's on the backside. So we've reversed the stereochemistry at that point. Okay. So apparently it didn't have any effect on the other stereocenter, the one with the methanol. That won't always be the case. Yeah. If, on the other hand, we have an SN1 reaction, then the first thing that's going to happen is this is an overall, excuse me. This slide gives you overall. You're going to have a mixture for an SN1, since the intermediate is a carbocation, then you can attack from the front side or the back side. Right? So you'll have a mixture of S and R isomers at that carbon. Some iodines on the front side, some on the back side. Now, if you get an equal, if you get a 50-50 mix, that's called a racemic mixture. And what that means is if you shine a polarized light through it, it won't rotate, right? Because one molecule rotates one way and the other molecule rotates back the other way. So you don't see any rotation in a racemic mixture. But this R and S are enantiomers of one another. They're mirror images, non-superimposable mirror images of one another. Now, what does that look like in terms of mechanism? Well, first thing has to happen is in an SN1 is the leaving group has to leave. So that produces looks like a tertiary carbocation, which is good because that's the most stable form of a carbocation. But still, it's very reactive. Now the iodine can attack front or back and produce an R isomer or an S isomer. If we look at it in terms of planes of symmetry, that confirms that the carbocation is non-chiral, right? Has a plane of symmetry right down the center of the molecule, including the phenyl group and the carbocation. So that means it can be attacked from either side and produce two different isomers. There's your racemic mixture. If the reactants and the environment, now that's another consideration we haven't talked about. We'll have to, that's going to come in the second term, where we discuss the environment in more detail. But if the reactants and the environment are achiral, then you get a racemic mixture. That is, you get equal amounts of both enantiomers. However, unequal amounts will occur. You get an unbalanced output of products if the reactants or the environment are chiral. So say you have a nucleophile that is itself racemic. Excuse me, not racemic, chiral. if it's a stereoisomer, then its attack will give you an uneven number of stereoisomers as a consequence of the attack. And the environment will also have an effect there. When I think of difference in environment, if you have a mixture of R and S isomers, and I think we talked about this earlier when we introduced the concept of thalidomide. One stereoisomer of thalidomide does what it's supposed to and reduces nausea for morning sickness. And the other isomer is the one that causes teratogenesis in the developing embryo. So the way you separate them is you have a column chromatograph, like a better one than we made in there. But the stationary phase is chiral. If the stationary phase is chiral, then it will be selective for one isomer versus the other, and that will separate them. So that's an example of a different environment. Now, the environment for the reaction, I think, depends on other factors also. Could be temperature, could be pressure. A number of factors could play in there and give you a non-racemic mixture. Okay. So I hinted at this a little earlier. When that, for an SN1 reaction, when that leaving group leaves, it doesn't leave all the way. It's like it hadn't left the house, right? It's still, you're cooking dinner and the leaving group is still right there behind you, the whole time watching over your shoulder, because it's a negative and the carbocation is positive. So the leaving group is going to stay very close to the side it left from. What that does, that ion pair, when the nucleophile attacks, it preferentially attacks from the backside, the opposite side from the leaving group. And that gives you an uneven percentage, an unbalanced percentage of stereoisomers. Only if you can get that leaving group far enough away can you attack evenly from both sides. Here's an example. In this case, we have, let's see. We have, let's see. Name that molecule. Name that reactant. It's going to be 1, 2, 3, 1, 2, 3, 4. 4 carbons. Butane 2-all. And then it's going to have a 1, 2, 3, 3 chloro. Yeah, 3 chloro. 2. Oh, and then a 1, 2, 3, 3 phenyl. So it's going to be a 3 chloro, 3 phenyl. And it happens to be, let's see, which direction is it going? Let's see. I think it's to the right. That's an S. Okay. So this molecule, under an SN1 mechanism, will produce a carbocation at that phenyl carbon group. I shouldn't say phenyl carbon because it's not on the phenyl ring. It's on the number 3 carbon. The number 3 carbon will be the carbocation, and it's not going to move, right? Because that's as stable as you can get. That's important, right? If it had formed on a secondary carbon, we might get a shift to a tertiary carbon if it's nearby. But in this case, it's already on a tertiary carbon. It's going to stay there. Okay, so what attack can happen? Well, front side attack or a back side attack, either way. Now we're not saying one side is preferential over another right now, but you will get these 2 isomers. Right? You'll get the 1, 2, 3. You'll get the 3S or the 3R iodo. Okay? But you've got a secondary, you've got another chiral center in there with the hydroxyl group. So that means you've already got a 2S hydroxyl in there, but it didn't change. So what does that mean about your outcome? That means you've got a they're not mirror images of each other. So that means they're diastereomers. So here we've produced diastereomers. Now this is a commonly used technique for a chemical reaction where you want to end up with a certain stereochemistry on a given carbon. So you add another stereocenter so that the outcome will be diastereomers. Diastereomers can be separated physically. Enantiomers can only be separated using a chiral matrix. But diastereomers are significantly different in their physical behavior. They're more easily separated. So keep that in mind when we get to next term. But the outcome here is a mixture of two diastereomers, and an unequal mixture at that. Okay. So this is trying to explain why you get unequal amounts. Well, first of all, we don't see a plane of symmetry there. Right? Let me take a closer look at that. OH, CH3H. Right. That's not a plane of symmetry, because if you draw that plane down the way they've done it, you don't have a mirror image on the right-hand side of the molecule and the left-hand side. On one side you have a hydroxyl, on the other side you have a hydrogen. So that's not a plane of symmetry. So when the iodine attacks on the right-hand side, you get the S isomer, and when it attacks on the left-hand side, you get the R isomer. But here's the other thing. Where's the hydroxyl group? If it attacks from the right, the hydroxyl group's in the way. If it attacks from the left, the hydrogen group is not quite as a big hindrance. So you're going to have a left side attack is preferable. It's going to give you a high percentage of product. So the 2s3r isomer should be more abundant. Let's see if that's what they said. No, they're not going to. He's not going to say. Maybe it's in the instructor's notes in the slide and I missed them. But that's what I would think. Right, the OH on the right-hand side would be a hindrance to the approach of that iodine. Everybody agree? Okay. Okay, so here we have, we're going to say this is an SN1 mechanism, and we've got two chiral centers. They're 2 carbons apart, and the iodine is the nucleophile. So if we produce a mixture, let's see, will the reaction produce a single stereoisomer, or will it produce a mixture of stereoisomers? I think it's safe to say it's going to be a mixture of stereoisomers. And will they produce isomers in equal amounts? And I say no, unequal amounts. So if we look at iodine is the nucleophile, leaving group is bromine. And if it's an SN1, bromine has to leave first. So on that carbon that bromine leaves behind, we're going to have a sp2 hybridized carbon, which means you can attack from either side. It's a carbocation. But what's in the way? On which side? On the back side, the methoxy group is in the way. So it should attack from the front side. the same side as the bromine. So you're going to have the same, you're going to have more, I think you're going to have more stereoisomers that are the same stereochemistry as the bromine was, and fewer of the opposite. Okay, so here we've got on that bottom slide, bottom part of the slide, you've got the carbocation, and then you've got the methoxy group sticking out the back. It's hindering the backside attack. So the front side attack, where the iodine comes in from our side, is going to be the dominant amount. Should be a higher percentage of the diastereomers. Since you've got two chiral centers in there, then we're going to produce diastereomers rather than enantiomers. Okay, how about an E2 reaction? So here we're going to eliminate. And E2 is bimolecular, happens in one step. So that means when the base attacks the hydrogen, the bond breaks with the carbon hydrogen. Those two electrons are sent over to the to make a pi bond between the two carbons, and the bromine leaves. So what's the preferential approach there? The preferential approach is anti to the bromine. And if we look at, let's see. Okay. Yes. Okay. So we only get one diastereomer. Now here's where the Newman projection comes in handy. If we take that carbon-carbon bond where we're going to put the pi bond and turn it 90 degrees and look at it as a Newman projection, let's see, they turned it from the top, they turned it clockwise. So that puts the bromine in the front on the bottom, puts the hydrogen in the back on the top, and it puts the phenyl groups opposite one another, which is where they should be. They're anti. That's the most stable form. Then the anti-attack then would take the hydrogen from the back, and the bromine would leave in the front, and it would produce the only diastereomer that we see from that previous slide. What other things can happen? Well, you can get rotation, right? Where you get the hydrogen and the bromine are gauche to one another on either side. That's called anti-coplanar. Excuse me. No. Anti-coplanar is the preferable way, where the hydrogen and the bromine are anti to one another. That's anti-coplanar versus the gauche arrangement. Now, I would suspect that it's entirely possible. Now, Dr. Carty says that only the anti-arrangement is going to produce that particular product. But this molecule can still rotate. I mean, it might not be there very long, but it can still, with the proper input of energy, could rotate around and give you another diastereomer. Let's see. That was the. Oh, we're still at E2. All right. This plane that's drawn through the molecule is drawn through the carbon-carbon bond that's going to have added to it a pi bond. So if we look at it in those terms, this also helps us understand what the outcome is going to be, because the hydrogen's plucked off, make a double bond, bromine leaves, And that leaves us with hydrogen out one end, methyl group out the other side, and the two phenyl groups are trans to each other. So this should be an E isomer, shouldn't it? Let's see if it's going to tell us that. Um, all right, this tries to explain why the E2 reaction is favored by anti-coplanar orientation of the substrates in terms of electrostatics. You want to get as far away from that leaving group because the leaving group is negatively, has a form of negative charge, right? And if a negative charge tries to come in there from the base and tries to attack a hydrogen, then it's going to feel some repulsion if they're in the coplanar arrangement rather than anti-coplanar. So this says we're going to get a mixture. Now, let me go back to the slide. This slide, stereo-specific. Okay, I misunderstood Dr. Carty. What he's saying is, for the anti-coplanar arrangement, you only get that one diastereomer. But you can still rotate around and theoretically get an approach from the coplanar. And that would put the phenyl groups on the same side of the double bond. Okay, so when we get to this description here on this slide, you can have, well, it's unlikely to get those phenyl groups on the same side of the molecule because there's so much steric hindrance. Right, so he may be right about that. You only get one diastereomer. But for this molecule, you've only got methyl groups and hydrogen groups. And so you can still get the coplanar approach rather than the anti-coplanar approach. But the anti-coplanar is the more stable one. And it's going to be the major product. So the E isomer is going to be the dominant product. The minor product is going to be the Z. But you will get those two diastereomers. Okay. I think we can skip this slide. I beat that horse enough. Now, if we go to E1, where the leaving group has to leave first. We were in E2, weren't we? Yes, we were in E2. E1. So the E1, the bromine has to leave, and that produces a carbocation. So then when the hydrogen is attacked, it neutralizes that carbocation with a pi bond. And we produce, again, it produces, the major product is still going to be the E versus the Z. And the primary reason for that, I think, is steric hindrance. Let's see if Dr. Carty agrees with me. All right, so we got the molecule there on the left, the starting, and it has to lose the bromine, and it makes a carbocation. We can still rotate around that single bond. If we rotate around, if we leave it the way it is, then we get the same outcome as the preferential E2 mechanism, major product. But with those phenyl groups, you've got a lot of steric hindrance, a lot of steric strain. So the molecule is not going to be coplanar. for very long. The attack is not a problem. It's the fact that the hindrance of those two phenyl groups tends to favor the anticoplanar. So again, the E1 mechanism is going to give you a mix of Z and E, with E being preferred. Now, my guess is that you're not going to have the same percentage of the mix, one over the other. And obviously, the E1 reaction is going to be a lot slower, much, much slower. All right. So we've looked at SN1, 2, E1, and E2 mechanisms, and the possibilities for each one in a multi-step reaction. But sometimes it's useful to add, we're sort of building our repertoire. The proton transfer step that we've studied and the carbocation rearrangement are useful to correct problems that may arise in a mechanistic sequence. But we have to put them in, we can't just throw them in willy-nilly. I mean, they have to be introduced in a logical fashion and something that makes sense and doesn't defy reality. So we've got some rules that help us, right? Rule number 1. I'll put the rule over here. Rule number 1 says, avoid simultaneous appearance of strong acids and strong bases. Avoid strong acid, strong base. I'll just leave it like that. So for a proton transfer step, which is very fast, right? Remember, in general chemistry, when you're doing acid-base titrations, you add a little bit of acid, a little bit of base, and you get a pH change like that. It's instantaneous. So adding a proton transfer step will not affect the overall rate of the reaction. Let's put it that way, because it's so fast. Now, how do you tell what's a strong base and what's a strong acid? Well, we compare them to, say you have, right, everybody knows this reaction. Right? The amphoteric nature of water. And this is going to have, let's see, like that, I believe. And this is going to be a formal charge of +1. Okay. So this has a certain strength of base. Since the K here is times 10 to the minus 14, then and this is both weak acid and weak base. This is going to be relative to these two water molecules. That would be a strong acid, strong base. But you can get bases that are stronger than that and acids that are stronger than that. And if any acid has a pKa of less than 0, what's the pKw here? 14. So if the acid has a pKa of less than 0, we can consider it a strong acid. If the conjugate base has a pKa that's greater than 14, that will be a strong base. And these are some examples. We can consider this a strong acid, a protonated methanol molecule. That's what the second one looks like. And let's see. Yeah. Oh, and then a deprotonated, is that right? Yeah. A deprotonated ethane molecule. Those are all strong acids. Why? Because they have pKa's that are less than 0. How about weak acids? Water's a weak acid, right? 10 to the 14th, or a pKa of 14. Ammonia is a weak acid. Ammonium, definitely a weak acid. And the methylamine is a weak acid. Strong bases. The hydroxyl is a strong base, right? And I had the name of this one last week, but I can't remember what it is. The H2N minus. The carbanion, CH3 minus, and the H minus. H minus is like that. So that makes it a strong base. And you can think of these in terms of, do they want a hydrogen, right? This one could pick up a hydrogen, right, and form a sigma bond. Or we could think of it in terms of Lewis acid, Lewis base. Right? This base is a electron pair donor. Right? That's a Lewis base rather than a hydrogen acceptor. And weak bases, obviously water is going to be both a weak base and a weak acid based upon this reaction right here. Ammonia is also a weak base. Chloride is, chloride's a weak base compared to what? Compared to the hydroxyl. Yeah. Chloride would be a weak base compared to the hydroxyl. Bromine, iodine, they'll be weak bases. HSO4 minus, HCO2 minus are weak bases compared to what? Compared to the hydroxyl. So if we look at this reaction and we see the reaction conditions are given on the arrow, right? The substrate is given as phenylmethanol or benzyl alcohol. And the nucleophile is the 2 carbons, ethane, 2 bromo ethane nitrile. And what we want to do here is create an ether. All right, so the conditions are basic. It's obvious because there's potassium hydroxide right there. Now, what about potassium? It's a spectator, right? So we would write the environmental conditions as having an OH minus in that environment. And why do we use DMSO? Remember what DMSO is? Dimethyl sulfoxide. So this environment is non-aqueous. We don't want waters in there. Now, if we try to use an SN2 mechanism here, then we would have to say that the hydroxyl would attack the carbon and bromine is the leaving group. And that would form what? Well, if it's an SN2, we have those two together and the leaving group is left. What have we got left behind? What we have left behind is a strong acid. Right? That middle thing, that's a strong acid because it's got the oxygen has a formal charge of +1 and it's got a hydrogen available to kick off, right? So it could be picked up by the hydroxyl, the KOH, right? The hydroxyl. That would short circuit the reaction, right? You would not get the products you want. You've got a basic environment with a strong acid in there, and the two are not compatible. So this reaction is unreasonable. Let's put it that way. It's not reasonable. Let's look at a reasonable reaction. Reasonable reaction would be first the proton transfer with the strong hydroxyl base. Picks up the proton and it makes an anion out of that oxygen. Now that oxygen is a rich nucleophile. It can attack the carbon and the bromine will leave. And when it does that, it forms a bond, a carbon-oxygen bond, that now we have our ether. That's a more reasonable approach. So if we try one way and we see that we have a strong acid in a basic environment, we know that that's not, we're going down the wrong rabbit hole. In this example, we have 2-methylpropane 2-ol. And this is an acidic environment with hydrogen bromide. Right? So both of those are strong acids. HBr and H2SO4, both strong acids. And the outcome that we have actually measured is 2-methyl-2-bromopropane. So the hydroxyl left and the bromine was substituted for that. Okay. This mechanism tries an SN1 route, a substitution with a unimolecular. Right? If we do that, then what has to leave? The only thing that can leave is the hydroxyl. So if the hydroxyl leaves, you've got a base in an acidic environment. That won't work. Right? So we can stop there. You don't even have to go any further. So instead, the hydroxyl does a proton transfer from the hydrogen bromide. Now we've got the bromide, the strong nucleophile, and we also have the heterolysis of that water molecule. Let's see. Hold on a second. Yeah, this is acidic environment, isn't it? Yeah, in acidic environment, we've got that strong acid group sticking out from the carbon, but it's going to leave. That's our leaving group. And why is it a good leaving group? Because water is very stable, right? You look at the aftermath. What comes after to see if the leaving group is good? If the after is stable, then you have a good leaving group. So we have stable water with a heterolysis. Now we've created a carbocation, which is the most stable of the carbocations, right? It's tertiary. Now the bromine can attack from either side. So this is a more reasonable mechanism simply because we're not producing any base in an acid environment. All right. Let's see. We're assuming this methoxycyclohexane in an acid environment, an aqueous acid environment, and we have to heat it. So this would have to be an elimination reaction because we're producing a pi bond. Okay. So what would be a reasonable mechanism for this? Well, it's an acid environment, right? So if we do, did it say E1? Yeah, an E1 mechanism. So the methoxy would have to leave and produce a carbocation. All right. How do we stabilize? Well, let's see. Is the water going to pick up that hydrogen? Well, it could, because this is an acid environment. But why is it unreasonable? Because our methoxy group is a base. Methoxy is a base in an acid environment, so that won't work. So instead, what we have to do is proton transfer from the sulfuric acid. All right. That proton, at least the first proton from sulfuric acid, is readily available. All right. So it attaches itself to the oxygen. Now we break and produce methanol. All right. We're not producing a base anymore. We're producing methanol by heterolysis, and then the hydrogen can eliminate. This is a more reasonable mechanism, simply because we don't have a conflict between a base and an acid environment. Okay. Here's another tempting fix to a problem. This oxyrane, which is ethylene oxide. Anybody ever use ethylene oxide? Operating rooms used to use autoclaves. They would take their utensils and put them in bags and autoclave them. And that would kill all the germs, right? And that would take, what, an hour, something like that. You have to go up to temperature, then you have to hold it for 15 minutes at 20 psi, and then you have to bring it back down. So what they discovered was if you put them in a bag that's permeable to ethylene oxide, you can put them in this chamber, squirt some ethylene oxide in there. In just a few minutes, you've killed all the bacteria, all the viruses, everything. And you can pull those out and vent the ethylene oxide outside so it'll pollute the environment. And then it's a very reactive molecule. Let me put it that way. Extremely reactive. One of the reasons is because it's that three-membered ring is very strained. Okay, so in this case, we've got a reaction that we know ethylene oxide with ammonia in an aqueous environment is going to produce 2-aminoethanol. So that means the ethanol is going to stay on the number 1 carbon, and then the ammonia is going to attach to the number 2 carbon. And we get 70% product there. Okay. So if we promote this procedure, this mechanism, where ammonia is in water, it's going to be slightly basic. So if ammonia attacks a carbon and breaks the bond and produces a negative oxygen on one end and a positive ammonia on the other end, how do we get to a neutral situation? Because this is not a stable molecule. Right? Well, Proton transfer would do it. Right? You take a proton off of the ammonia, make an amine group, and put it on the oxygen. Right? But how do we get there? How do we move that proton? Well, the temptation is to, with curly arrows, break the bond with the hydrogen and form the bond with a lone pair donated from the oxygen. But look how far away they are from each other. Right? They're 2 carbons away. That never happens. You can't do that. Right? Not on this size molecule. Okay. If you have a big molecule that has sigma bonds and it can rotate and twist around, it may be possible to do that, but not with this molecule. So this intramolecular proton transfer is not reasonable. So look at the environment. It's an aqueous environment. Right? We have the ability now to for an intermediate with water molecules. So what we do is we transfer a proton to that oxygen from a water molecule. That makes a base. And the base attacks a hydrogen that's on the ammonia and reconstitutes itself. So you have 2 proton transfers, and that solves the problem. And remember, proton transfers happen very quickly. So this is what's known as a solvent-mediated proton transfer. If you didn't want that to happen, then you would not have an aqueous environment. Right? You'd have a non-aqueous environment or a non-proton environment. Oh, I skipped rule 2, avoid intramolecular proton transfer. Avoid intramolecular proton transfer. Notice we say avoid. With large molecules, it's possible. Okay. Rule number 3. And I've already mentioned this one. Avoid termolecular steps. It's just kinetically unreasonable to have 3 groups coming together at one time. So here we have a termolecular step where water is approaching from one side and we're doing the proton transfer from the other side. And then we're, so how many arrows we got there? 1, 2, 3, 4. We violated the 3 arrow rule too. Right? That may be why one of the reasons that 4 arrows are unreasonable. Carbocation rearrangements. All right, remember why these arrangements are necessary. If the reaction produces an intermediate where the carbocation is located on a primary or a secondary carbon and a tertiary is available next door to the very second carbon, then it's very likely that you will transfer that carbocation to the tertiary because it's more stable by one of 2 mechanisms, either a methyl shift, a 1,2 methyl shift, or a 1,2 hydride shift. Okay. So for this SN1 reaction, which means that the leaving group has to go. The iodine has to go first. Then where does that leave the carbocation? It leaves it on that number 2 carbon, right, where the iodine left. But we know that the hydroxyl, the substitution, is going to end up on the number 3 carbon, right? We have proof of that. So how did that happen? Well, here's how it happened. With an SN1 reaction, the leaving group leaves, and you have a secondary carbocation left behind. Now you get a 1,2 hydride shift that moves the carbocation over to a more stable position, in a tertiary position. Now the water attacks, right? It has those lone pairs on the oxygen. It attacks, forms a bond, and now we've got a +1 formal charge on the oxygen. So it breaks the bond with one of the hydrogens and transfers that over to another water molecule. And that leaves the hydroxyl on the second carbon, on the number 3 carbon. Okay. That's a 1,2 hydride shift that explains the outcome for that reaction in an SN1 mechanism. All right. So the fourth rule is rule 4. And these rules are valuable through the next term, right? Remember these rules. If an energetically favorable 1,2 hydride shift or 1,2 methyl shift competes with another possible elementary step, the rearrangement is faster. So if there are other possibilities, and you have the possibility to do a 1,2 hydride or a 1,2 methyl shift, do that one first. And then see what the next step is, what's the next favorable step. So in this SN1 example, we get actually a tertiary, we get a tertiary carbocation. So what's the outcome here? Well, 1, 2, 3, tertiary. If it moves over to, okay, now we're not just talking about a 1,2 methyl shift to stabilize the carbocation, but now the carbocation is going to be close to a phenyl group. And remember, double bonds and phenyl groups are electron donators. So they will stabilize that carbocation. So rather than the 1,2 hydride shift would not make sense, because it would put the carbocation on a primary carbon. That just won't work. So a methyl shift will put the charge on a carbon that can resonate with the phenyl group, right? So I misspoke. It's not so much electron donating as it is the possibility to resonate with the phenyl group. And that resonance with the phenyl group places the carbocation on the alpha carbon off of the phenyl. Then what you can do is attack with your methanol. And at that point, you want to transfer a proton. And that forms the ether. So there, the hydride shift didn't make any sense. The methyl shift did make sense. So here we have another example of resonance stabilization of intermediates. We know that 2-methyl-but-3-ene-2-ol in concentrated hydrochloric acid will give us 96% 1-chloro 3-methyl-but-2-ene. So the leaving group is going to be the hydroxyl somehow or other. And it's going to leave us with a double bond. We're going to keep the double bond, but now the chlorine is going to be on the number one carbon. Actually, no. Well, yeah, the numbering switches. Notice that when we get the new compound, the numbering switches from the left-hand side. Now it switches to the right-hand side because we've added the chlorine. Okay. So the substitution, if this is an SN1 reaction, the substitution didn't take place on the carbon with the leaving group. That's where we would expect it. So we got to explain why. Why didn't it occur on the carbon where the hydroxyl left? And there's no carbocation rearrangement that we can discern. So how do we explain the product? Well, what happens is we get a proton transfer first. Remember, this can happen very fast. Proton transfer happens faster than the OH can leave. But once we get the proton transfer, then we produce an exceptionally good leaving group, right? Water is a much better leaving group than hydroxyl. And let's see, let me look at the environment again. This is an acidic environment, right? You're not going to produce a hydroxyl, right? If the hydroxyl leaves, it's a base in an acid environment. That won't work. So we have to do a proton transfer. That's the only thing that's reasonable now. Then you can have a water leaving group. That'd be great. And you're left with chlorine. Okay, so what does the chlorine do? Well, the chlorine can attack, right? The chlorine can attack because we left behind a carbocation. But there's resonance available, right? We can resonate in such a way that we have two possible structures. And remember, when we write these resonance structures, they're a visualization. They're not reality. Reality is something in between. Let's see, get that out of my way. Okay. And the interconversion that we represent as a resonance structure is not an elementary step. And I just mentioned the reason for that, because we're not saying that we go from one to the other and back and forth. It's something in between. So which one is the nucleophile going to attack? The carbocation that's secondary, actually tertiary, or the carbocation in the resonance structure that is primary? Well, the more reactive one is primary, and the least hindered one. There's less steric hindrance with the primary carbocation. So resonance gives us the opportunity to attack that number one carbon instead. That seems counterintuitive, but when you think about the reactivity, then it does make sense. And that's the most reasonable explanation for the data that we got, which says that outcome is 96%. Right? It doesn't matter how much logic you pour into it, you can't defy the reality. So this is our explanation. This resonance gives us a primary carbocation that is extremely reactive and available for the chloride to attack. All right. So I'm not sure what this slide's good for. First resonance structure. Oh, Okay. All right. I was looking at it from a different angle, right? I was attacking the primary carbocation, but if we attack that first carbon, then that frees up the pi electrons to form a double bond. You know, that scenario does make more sense than it does my other. This is one way to represent it, but I think what actually happens is once we get that bond formed with this carbocation, since they're both uh, resonating, then now we have a situation where we've got to do something with those extra electrons, and that's where uh, the pi bond shifts uh, two carbons. I said it, but I didn't write it. Um, when hydride or meth shifts are available, they win. That's it.